Hi, I'm Adithya Rao, and we did the filters project, and I assisted on tasks 1 through 3 and 5 through 7. Distorted signal. The user is able to construct this signal by entering in the frequency, amplitude, and phase. Later, we add a random number of random frequencies to the original signal in order to add noise to it. The remainder of the program consists of solving transfer functions for the filters that the user has chosen. The options that are given to the user include using a single low-pass filter, high-pass filter, or pass-band filter. They're also given the option of using a combination of low-pass and high-pass together. Nevertheless, once the user has selected a filter and the program has calculated the transfer function for the filter, the user is asked if he or she would like to implement the transfer function or filter. If they select yes, the distorted signal is passed through the filter and certain unwanted frequencies are eliminated. Finally, we're left with a less distorted signal, and we can compare it to the original signal that was made in the beginning of the program.
I'm Ajit Punj, and I completed tests 1 through 3 and 5 through 7. Amplitude, phase, and frequency. This while loop encompasses all of task 2 and will run as long as n input is not set to 1. Initially it is set to 0, and at the end, if all the checks pass through correctly, then n input is set to 1, which will break out of the while loop. After each input, the program will check to make sure it is a valid input. If it's not, n input will be set to 0 and the while loop will repeat, meaning that the user will have to input again. After all the inputs are checked and verified, the constants are set, which are set over here, dt, k, t, p, and all of them will be calculated. Then at the end, the if statements over here decide whether it'll be whether sine graphs or cosine graphs will be used, and based off the inputs that were selected in the first part of task 2. 3, n is set to a random integer between 3 and 10, and that'll determine the number of random frequencies. Next in task 3, I have a while loop that encompasses all of the vector generator that will make sure that none of the elements are repeated. So this line right here generates the vector that'll have numbers between that'll generate the random frequencies between 0 and 256, and they will be doubles and not just integers. This for loop within a for loop right here will check to make sure that it'll check every element of the vector and make sure none of them are repeated. If none of them are repeated, if any of them are repeated, check 3 is set to 1, and that goes over here in this if statement. If check 3 is equal to 1 at any point, then the while loop random generator will be reset to 0, which will make the while loop repeat itself. And if not, random generator will set to 1, and it'll break out of the while loop. Loop will run through every element 1 through n, and it'll create n different frequencies in the vector, so it basically creates a noise for every element of the array. And so then you have an array with each time and each frequency, and this will sum it up and set it to S noise. And S new is then set to S plus S noise, which adds the noise to the original signal.
Hey, my name is Naveed Edalati, and I did tasks 4 and 8 through 12. In task 4, we're transforming the signals into frequency domain from time domain, the original one and the noisy one. Here's the most important line of code, which is making relationship between frequency and time. Practically what we're doing is we're going through every element in our time vector and relating it through frequency by the relationship f equals 1 over t. Over here we're just plotting the original signal and the new signals in the same figure in time domain and frequency domain.
He or she would like to use. So filter selection would either be 1, 2, 3, 4, or 5. 1 for low pass, 2 for high pass, 3 for pass band, 4 for low pass then high pass, and 5 for high pass then low pass. Task 10, they are similar, so task 10 asks the user if they're satisfied with their inputs. If not, it will ask them to input them again. If yes, then it will continue through the program. So the variable task 10 up top is set to 0, and the while loop encompasses all of task 6, and it'll keep running through as long as task 10 is not set to 0, set to 1, which means that if the user selects that they are not satisfied, task 10 will be reset to 0 and the while loop will repeat. So if the user selected high pass or low pass in task 5, the program will prompt the user for a cutoff frequency, which is then translated to omega c by multiplying by 2 pi. And it will also ask for gain. If the user selected passband filter or a combination of high pass and low pass, then the frequency it will ask for center frequency and gain, and that's for passband. Gain is asked if it is passband, and if it's a combo of high pass and low pass, then it's asked. Then the program prompts the user to set gain per, which is the gain for the high pass and low pass. The program close the figure and clear the command window.
So task 8, we're calculating the resistance and capacitance of the filters given the cutoff frequency, the gain, or the center frequency and the passband. We were also given the resistance of certain resistors. So here's the calculation for low pass, the high pass, and the passband. Over here it's a little bit more complicated. We're doing the combination of the two filters. So the equations are similar because we're using the low pass filter, then a high pass filter, or the opposite in order. The only difference is that we're using the lower end of the passband for the low pass filter and the higher end of the passband as input for high pass filter. And we get those lower and higher ends of the passbands by subtracting half of the passband by the center frequency or adding half of the passband to the center frequency. So task 9 is solving the transfer functions. Before we do that, we have to set a range where we want to solve the transfer functions, and that was 1024 elements over the range 0 to 0.5 over dt using linspace, and we did that because we don't want to get a dimension error later when we multiply the transfer function by the signal. And what we're doing here is translating this vector into omega by multiplying it by 2 pi. Then we're solving for each low pass, high pass, and passband and combination filters, plotting them on a log-log based graph against omega. Only difference for the combination is that we're going to have two transfer functions, one low, one high, one using the lower end of the pass band and one using the higher end of the pass band. Of code is tasks 10, 11, and 12 for the low pass, high pass, and passband options. Practically what we're doing is applying the filter here, so we multiply the transfer function by the noisy signal in frequency domain, and we translate the output signal we're getting from the filter into time domain, and then we plot our output signal against our original signal in the same plot. In task 12, simply what we're doing is compensating any amplification, dividing by the gain, and plotting the less amplified output signal against the original signal. Here what we're doing is calculating the mean percent difference, and the user is later prompted with all their information, including the mean percent difference. Here we're doing tasks 10, 11, and 12 for the combination of the two filters. First what we're doing is multiplying the noisy signal by the low pass transfer function. Then we're getting an output from the low pass filter and multiplying it by the high pass transfer function, and then we finally get our final output, which we transform into time domain, and we graph it against our original signal. Then we take any gain out by dividing by the gain per filter, compensate for amplification, and graph it against our original signal, and also get the mean percent difference from the scaled versus the original signal. Here we're doing quite the similar thing, except for high pass first. Theoretically, the order of the two filters does not matter, but our program is order sensitive. And that's the end of our program. Thank you.